Hello everyone. So on our derivative of product and quotient rule, in that series I'm going to look at trigonometric functions and then also look at higher order derivatives. Okay, so here's the list. We have already learned how to find the differential of sine and cosine, and also in the previous video I was talking about differential of tangent. So these three are already there. So the next three, differential of cotangent is minus cosecant square x, differential of secant x is tangent x secant x, and differential of cosecant x is negative cotangent x times cosecant x. So let's look at an example. So we want to find the differential of y equals 2 times tangent x minus secant x. The differential is, remember differential of, it's a constant times the function tangent. You keep the constant out, take the differential of tangent, which is 2 times secant square x, and negative times, it's a difference of two functions. So differential of secant is secant x tangent x. Now clearly you can see secant is common in both these terms. You can take the secant out. What you're left with is 2 times secant x minus tangent x, and that's where you can leave. Now let's go ahead and find the derivative of another function. And this time we can also evaluate the function value at a certain point. So if you're given a function sin x times sin x plus cosine x, clearly it's a product of two functions, sin x with sin x and cosine x. And we would like to evaluate this derivative at a point pi, 4, and 1. Now we could have multiplied and then did the work, but then it will involve certain other rules which we have not yet learned. So this will help us to practice our product rule and then derivatives. Okay, so the first thing we're going to do, as I said, we're going to apply the product rule. So remember, this is the first function, this is the second function. So we take the differential of the first, which is sin x prime, times the second function sin x plus cosine x, plus keep the first function sin x and differential of the second, which is sin x plus cosine x. Go ahead, apply the differential. So it is cosine x times sin x plus cosine x. In the second expression, sin x, and if you're taking the differential of sin x plus cosine, it's going to be cosine minus sine. Differential of cosine, remember, is negative sine. Now after this is simple algebra. We just multiply cosine with this expression inside and sine with this expression. What we get is cosine times sine plus cosine with cosine plus sin x with cosine x minus sin x and sin x. So what you're getting is, if you notice, cosine x times sin x. Now remember, cosine x and cosine x is cosine square x or cosine x, or however you want to write it, plus sin x cosine x and minus sin x squared. Now cosine x and sin x are basically the same. It doesn't matter you put the cosine first or the sine. It does not matter. So what you get is you add these two expressions. They're the same. So you say 2 times cosine x sin x plus cosine square x minus sine square x. You can also write it like this. Cosine square x minus sine square x plus 2 cosine x sine x. Okay? Now, remember, the question says evaluate this derivative at the point pi, 4, and 1. So I could have done this way, but I prefer to keep it in the form as I've written here. The reason is because when you evaluate the derivatives at a point, this makes life much more simpler. Okay? So keeping that, so we're going to evaluate at the given point. So remember, the point is pi, 4, and 1. Okay, so f prime at pi 4 is what? 2 times cosine pi 4 sine pi 4 plus cosine pi 4 the whole square minus sine pi 4 the whole square. Now remember, cosine pi 4 and sine pi 4, basically the value is square root 2 over 2. And so the last two terms are basically cancelling out in terms when you plug in the values. The first expression says 2 times cosine, that is 2 times square root 2 over 2 times square root 2 over 2. So this 2 and 2 cancels, the square root 2 with the square root 2 with this cancel, you're left with a 1. Now, I would like you guys to practice some of these problems 0.6 of them. So please go ahead, practice them, and make sure you keep the differential form, the table of trigonometric functions in front of you when you're doing it. Okay, let's go ahead and look at now higher order derivatives. This is very, very simple, guys. It's basically like you're taking a derivative of a derivative. That simply it means higher order derivatives. So start with a very simple example. So when we take the derivative of this function f of x, which is x5, we write it as f prime of x, which is 5x4. So this is called the first derivative. Now if I take the derivative, remember derivative is a function. So this f prime x is a function. Instead of writing it as f prime of x, I could have written it as h of x. It's a function. It's just the notation, but this makes our life simpler. Now if I take the differential of this function, that means I'm taking a differential, which basically means f prime of x, the whole derivative. That's what it means. So the notation is f double prime of x. That's what it means. So if I had written f prime of x as hx, then that would become h prime of x. That's what it would mean. So if you take the derivative of this function f prime of x, which is 5x4, we get 20x cubed. That's the second derivative. Now I take the third derivative, in other words, derivative of this function, you get 60x squared. That's f triple prime x. Then we take the derivative of this function. Now when you take the fourth derivative, the convention is to write it in this form. F, and you put the 4 in parentheses, and you get 120x. And as you see, you continue down. One observation. Notice when you're having a nice little polynomial with a positive exponent, every time you take a derivative, notice it is going down, one value down. So if it was x to the fifth, the first derivative would make it x fourth. The second derivative would make it x cubed. Third would make it x squared. Just an observation, guys. It will come in handy later on. Okay. Now the next slide basically is all these notations and how do you write it down. Many forms. First derivative is y prime, f prime of x, dy by dx, ddx of f of x, dx of y. Now, these are the ones, if you notice, I kind of prefer to use y primes, more concise, easy to work with. Similarly, second derivative, y double prime or f double prime of x, which is d2y over dx squared. So let me just talk about this. This basically means ddx of dy by dx. So notice, d and d are basically getting together and becomes d squared. Dx and dx is the whole square. So this is dx squared. Similarly, y triple prime, d cubed y over dx cubed, fourth derivative, and so on. If I take the nth derivative, it is y to the, so nth with n in parentheses, and dny over dxn. Okay, let's do an example. So find the second derivative of these functions, y equals x cubed plus 32x. So if the first derivative means 3x squared plus 32, the second derivative is 6x. Okay, let's look at the trigonometric function secant x. So you take the first derivative, it is secant x tangent x. Now when you take the second derivative, remember now this expression is a product of two terms, the first term and the second term. So you're going to take the derivative. So when you take the second derivative, the product rule comes in play. So secant x derivative times tangent x plus secant x times differential of tangent x. Now you apply the derivative of secant x gives us secant x tangent x times tangent x plus secant x times, forgot to write this one. It's secant x, so there is secant x. It's a little typo, guys. So that was because the next one this would become secant x is common in this whole expression. So I take the secant x out. So you have tangent square x. See the mistake I'm having, and plus secant square x. Okay. Because this expression, guys, remember, is secant cube x. Okay, once again, practice time. So 5 questions for you to practice finding the second derivatives. Now let's go ahead and look at an application of a higher order derivative. Remember we talked about earlier in one of the previous lectures of application of the derivatives, which we talked about rate of change, and there we talked about velocity, which was the differential of the position function s of t. So we're going to work on that here. So remember when we looked at derivative as a rate of change of one variable with respect to another variable. Examples were growth rates, velocity, acceleration, production rates, and so forth. Now remember, velocity function v of t was the differential of the position function s of t. Now if I take the differential of the velocity function, so that means if I take v prime of t, this is called acceleration, which is basically taking two derivatives of the position function, which is s double prime of t. So as I said, acceleration is basically differentiating position function twice. So the next slide gives you a nice little nicer looking way of how these functions are related. A position function is s of t, its derivative is velocity function. The derivative of the velocity is the acceleration function. So one example. So we know the moon has no atmosphere, so a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. Now the position for each of these functions falling objects was given by s of t is negative 0.81 t squared plus 2, where s of t is the height in meters and t is the time in seconds. The question is, what is the ratio of the Earth's gravitational force to the moon? Okay, when looking at gravitational, remember gravitational force is given by s double prime of t. So let's go ahead and do that. Now to find the acceleration, we differentiate the position function twice. The first time we differentiate this position function, we get negative 1.62 t. Second time we get negative 1.62. Now remember the second derivative is negative g, that is the acceleration due to gravity on the moon is now g is 1.62. Negative is because it goes in the opposite direction here. So the acceleration is meters per second per second. Now the question was, what is the ratio of the Earth's gravitational force to the moon? Now the Earth's gravitational force we know is 9.8 meters per second, and the moon's gravitational force, which we just found, was 1.62. So the ratio of Earth's gravitational force to the moon's gravitational force is approximately 6. Now let's look at some sketching, because we know we can show graphs of these functions. Okay, we like to sketch the graph of f prime of x and f double prime of x for this function below. Remember earlier I said, let's talk about this one. Remember we talked about fx x to the 5. So we say if we took the first derivative, what happened? We had 5x4. Remember, it was a fifth order polynomial. The first derivative became 1 less, which is now 4th degree polynomial. And if I take the second derivative, this became a polynomial of, it was 20x cubed. This went on. So this was an example I had started with when we talked with higher order derivatives. So the idea is that every time you take first derivative, you go 1 degree down in terms of the polynomial. So come over here, what do we notice here? Our graph over here, so let me just make a little difference. So this is f1, f1 prime, f1 double prime. It's a different function than this function f here. Now this function f, which is given below, guys, what function is this? It's a squaring function. It's a function, notice, which is an upside down parabola. So suppose we know this is a second order polynomial, isn't it? So our f of x here is minus x squared. Suppose it is because it's an upside down parabola, that means it's a negative x squared. Okay. So I'm just assuming, suppose it's a squaring function, but it will definitely have some more terms. But at this point, I'm assuming I'm taking my life simple, so that because I have to sketch the graph. So fx is minus x squared. So f double prime would be what? F prime would be what? Negative 2x, which is the graph of this f prime is what? A straight line. But it has a negative in the front of x. That means it's a straight line going down. So eyeball it and you say, hey, this is f prime. The sketch of f prime is a straight line. The only thing you have to keep in mind is because it is negative, that means this derivative graph is going to be straight line going down. Okay, if I take the second derivative, so you just have to eyeball it just to have an idea, bigger picture. Look at the bigger picture, okay? So the second derivative is the constant function negative 2. Remember, I just assumed this is, remember this example is not exactly negative x squared. It's negative x squared plus something. So, but at this point, when you are asked to sketch the graphs, I just want you to look at the bigger picture, that this first derivative is going to be a straight line going down, and the second derivative is going to be a horizontal line in the y-axis, in these below the x-axis. So it's somewhere over here. So here is your sketch of f double prime. In other words, I want you to just eyeball how the graph would look like. What I'm trying to let you know is that every time you take a polynomial and you take a derivative of the polynomial, it goes 1 degree down. So you have to keep in mind, if the original polynomial is a squaring function, the first derivative is going to be a linear function, and a linear function graph is a line. The only thing you have to keep in mind is the line going up or down? So if I take this derivative of this derivative, that means I'm taking the derivative of this linear function, it is going to be a constant function. And the constant function either will be above the x-axis or below the x-axis. Now over here, it's going to be below the x-axis because the constant, remember, if a line goes down, that means the constant is going to be having a negative in its expression. And that's the bigger picture. Okay, a very special case of functions, guys, which we are going to look at now here. Okay, now we are given a graph of two functions f and g, and we are also saying we have to consider, we create two new graphs. A function which is a product of these two, f and g, is going to call p of x, and q of x is a quotient of two functions. And we will like to use these graphs to find the value of p prime of 1 and q prime of 4. Okay, before we do p prime 1 and q prime 4, let's go to the original. You have px is the product of two functions. We just learned the product and the quotient rule. So what is p prime of x going to be? It's going to be f prime of x, g of x, plus f of x times g prime of x. Remember that. So when I want to find p prime of 1, what basically I'm saying, wherever your x is, put 1 there. So it's going to be f prime of 1, g of 1, plus f of 1 and g prime of 1. Also keep in mind, f prime is the slope of the tangent line to the graph of the function at that point. So if I look at this graph, so this graph f, this is a straight line. So the slope of a straight line basically would be the slope of the straight line at any point on the graph of the function. Okay, so that's what you have to keep in mind. So we're looking at f. So before I do f prime of 1 and g prime of 1, I'm going to look at g of 1. What g of 1 means? Evaluate the function g at 1. Now here's my 1. So what is g of 1? It's 4. Do you see that here? So g of 1 is a 4 plus. What is f of 1? F of 1, remember this is 1 f of 1 is this point. That is f of 1, which is a 6. So now we have to fill in g prime of 1 and f prime of 1. Notice, this is what that means. What is f prime of 1? It means if it is the slope of the tangent line to the graph of the function at x equals 1. And because this is a line, so f prime is nothing but the slope of the line. So what is the slope of f of 1? Look at this one. So we need to find the slope. So what is the slope of this line? What do you think is the slope, guys? The slope is 1. Notice, you go 1 rise and you go 1 up. So the slope of f prime of 1 is 1. That's it. What's g prime of 1? Notice the graph g at this point, it's going down. So what is this? What is the slope at this point? That means the slope of this line. Notice, so what is the slope over here, guys? Okay, so we're saying this one. Let's look at this one. What happens? You go 1 down and then you move, run is, remember the slope is rise over the run. So 1 down and 2 you have to move. So what is the slope? Because the line is negative, it is negative 1 over 2. So what is your final answer? It is 4 times plus minus 3. So the final answer is a 1. Okay, let's look at q prime of 4. Now remember once again the formula I told you. So I'm going to write this down, formula again. So q prime is g squared f prime g minus f g prime. Okay, so q prime of 4 is going to be what? It's going to be g of x, the g of 4, the whole square. Remember, x is now going to be replaced by 4. Let me just write it much more. So, okay, q prime of x. Let's write down here. G of x, the whole square. So it's f prime of x, g of x minus f of x times g prime x. Now replace x by 4, so you have f prime of 4 times g of 4 minus f of 4 times g prime 4. Okay, now let's go to the number 4 on the x-axis. That's it. So what is g of 4? G of 4 is a 2. So it's 2 squared. Okay, let me be consistent with the colors here. So g of 4, remember, let me use, say, blue here. G of 4, that's g of 4, guys, which is a 2. Okay, now g of 4 is a 2 minus, now what is f of 4? So you go up, f of 4 is a 7. That's f of 4. So minus 7. Now times. Now what is g prime of 4? Now remember, where is 4? That means that is the slope of the tangent line to the graph of the function at 4. Now what is the graph at this point? It's horizontal. That means horizontal line, the slope is 0. So g prime of 4 is 0. Now let's look at this. F of 4. The graph is going down and it goes 1 down and it goes 1 in the run. Rise over the run, the slope. So it is negative 1. Oh, sorry, g of 4 is a 3. Sorry, it's not a 2, guys. It's 3. I'm sorry. This one is a 3. Yeah, my mistake. Let me correct the numbers. This is 3, guys, not 2. This one is 3. I didn't realize it. Okay, good. I'm glad I caught it up. Okay, so f prime of 4 we said is -1. So what's the final answer? It's -3 over 9, and the final answer is -1/3. Okay, so these are some of the kind of problems which are basically applying things you have learned from a graphical point of view. So kind of these things can come in the exams. Okay, so here's the practice time for you. We've talked about sketching the graph of f prime and f double prime earlier. So you have another parabola. See what would be the sketches of the f prime and f double prime. And then what you're given is a graph of a function g prime. Remember, it's a g prime. That means this parabola is g prime. And you're asked to find g prime of 0, g prime of 3. That means what is the value of the function of g prime when x is 0? What is the value of the function of g prime when x is 3? Remember, the derivative of a function is a function. Okay, another kind of questions is if you're given a function fx which is 2gx plus hx, find f prime of 2. Very similar to just the problem I did earlier, which was in the product and the quotient rules. Here, notice it's the sum of two functions. So apply the same idea. Thank you.